5:30 virtual session tomorrow.
So we have some force example questions that I'd like to go over. The first one says we have a 500 kilogram car that is traveling at 15 meters per second and experiences a net forward force of 1,417 newtons for 3 seconds. We have a lot of givens in here, and we still follow our guess problem solving steps, but now we're going to include free body diagrams as part of that guess problem solving piece. So in our givens, I see a mass of 500 kilograms. Kilograms are always mass and newtons are always force. It's traveling at this speed and experiences a net forward force. So this would be my V original, 15 meters per second. And this is the net force. The net force is a combination of all the forces. It's not an individual force. So the net force in the x direction is 1,417 newtons. Time here is 3 seconds. Let's go ahead and draw a free body diagram for this situation. So it's a car. We must have some engine applied push force forward, and then there's going to be some resistance force backwards. The car has some weight, which is the force of gravity. Remember, weight and force of gravity mean the same thing. And then my car is not falling through the pavement, nor is it accelerating up into the sky, so the forces must be balanced in that y direction. Here's my normal force. I then also want to go ahead and write my Newton's second law equations for this free body diagram. So the net force vertically in the y direction would be all of the forces up. I see the normal force in my free body diagram, minus all the forces down, force of gravity, and that's equal to the mass times the acceleration vertically in the y direction. And then the net force in the x direction is equal to everything forward, that's the engine force, minus everything backward, the resistance force, and that's equal to the mass times the acceleration in the x. Last thing I want to do is think about, is anything in these equations zero? Well, the forces in the vertical direction are balanced because there is no acceleration up or down for this car. So I'm going to show that that acceleration in the y direction has canceled out to zero. There is an acceleration in the x direction. This car is speeding up, so we leave that. And then finally, we know that in our first unit, the motion unit, we had 5 sets of variables. And now in this new unit, our force unit, we have 3 variables also. What I want to do is classify all of my givens as either a motion variable or a force variable to help me figure out the process I'm going to use to answer this question. So I'm going to use my yellow highlighter to represent motion variables, and I'm going to represent force variables with my blue highlighter, and that'll just help us get a bigger picture of what's going on. So then let's go through and classify. Mass, kilograms, that's a force variable, so I'm going to highlight that in blue. V original was a motion variable. I'll highlight that in yellow. Net force, well, it's a force, so blue highlight. Time, that's a motion variable, so I give that a yellow highlight. Okay, now we are ready to start the question. Part A, it says, what is the weight of the car? So part A, weight is force of gravity. And so I've got 2 ideas here. I have the force of gravity and the normal force. When you subtract those, they're 0. I don't know the normal force, so I can't use that piece. But I do also have a relationship between the acceleration of gravity and mass. So the weight, force of gravity, is mass times gravity. I have been provided the mass. So 500 kilograms times 10 meters per second squared. Kilogram meter per second squared is a newton, so that's 5,000 newtons. So 5,000 newtons is a force variable, so I'm going to go ahead and highlight that, remind myself that that's a force. Part B says find the normal force. Well, I actually have that equation written out already. So the normal force minus the weight is equal to 0, which means that the normal force is equal to the weight, equal in opposite direction. So the normal force would be 5,000 newtons up, and the weight is 5,000 newtons down. Highlight that blue because it's a force. Part C, what is the forward acceleration of the car? Forward, that just means that we're looking in the x direction. So part C, acceleration in the x direction, question mark. Well, acceleration is this unique variable that has dual personality. It is a motion variable, but it's also a force variable. I know that I need 3 givens to use a motion equation. And as I look at my highlight here, I only have 2 givens in the motion direction, so I can't use a motion equation to solve for acceleration. But I do have one other piece available to me, my forces. Net force is equal to mass times acceleration. They did give me net force, they did give me mass, so I can use this relationship to find acceleration. I'm going to rewrite that equation first. Acceleration in the x direction is the net force in the x direction divided by the mass. So that's 1,417 newtons divided by 500 kilograms. 28.34, so 28.3 meters per second squared. Okay, acceleration. Again, it's a motion variable and a force variable. So when I highlight this, I'm going to represent that dual nature by highlighting it both yellow and blue. So that brings us to part D. It says, what is the final velocity of the car? So part D, V final is my unknown. V final is a motion variable, so I do need to use a motion equation. I have 3 givens, and displacement is not part of this question, so I'm going to use the equation without displacement. V final equals V original plus acceleration multiplied by time, 15 meters per second, plus the acceleration, 28.3 meters per second squared multiplied by that time of 3 seconds. I'm getting 99.9, so I'm going to round that to 100 meters per second. And this is a motion number, so I'm going to highlight that in yellow. And then I'm going to add one more part to this question. So part E, let's go ahead and write it out. If the engine provides 2,000 newtons of force, how large is the resistance force? So 2,000 newtons of force is this engine force, and I can go ahead and label that in my free body diagram if I'd like. It helps me organize everything. And that is a force value, so I'm going to highlight that in blue. We're looking for the resistance force. We're looking for this force over here. I already have the equation written out on my page here. So I know that the net force is equal to the engine force minus the resistance force. And I have all of those values. So I can go ahead and rearrange the equation for my unknown. So that resistive force is equal to the engine force minus the net force in the x direction. Substituting my values in, 2,000 newtons minus the 1,417 newtons. And I am getting 583 newtons. Now let's look at the second example question. We have the mass of a plane, and it lands with 125 meter per second velocity, and it slows to a stop in 20 seconds. So starting with my givens, the mass is 1,400 kilograms. V original, this is the landing speed, but then it slows to a stop, so V final would be 0. So V original is 125 meters per second. V final is 0 meters per second, and then the time here is 20 seconds. If we think about our free body diagram, the plane is moving forward, but what the plane is going to do is apply the brakes. So the force of the brakes would be a backward force. We would have the weight of the plane, the force of gravity, and then also the support force of the ground on the plane, which we call the normal force. Newton's second law equations, the net force vertically in the y direction would be all the forces up, my normal force minus all the forces down, the weight, and that's equal to mass times the acceleration in the y. And then the net force in the x direction would be all the forces forwards. Well, I don't see any, so that's 0, minus everything backwards, that's the braking force, and that's equal to mass times the acceleration in the x direction. Now, if I want to classify everything as either a force variable or a motion variable, mass is force. I'm going to highlight that in blue for forces. V original, that's a motion variable. Highlight that one in yellow. V final and time are also motion variables, so they're going to get the yellow highlight. Okay, those are my givens. Now I'm ready to answer these questions. Part A, what is the length of the runway that is used by this plane to slow to a stop? So part A, displacement is my unknown variable. Displacement is definitely a motion variable. I look over here, I do have 3 givens provided for motion, so I can use that motion equation. Acceleration is not one of my variables, so I use the motion equation that does not include acceleration. Displacement is equal to V original plus V final. Everything multiplied by time and then divided by 2. The equation is already in the correct form, so I skip ahead to my substitution step. 125 meters per second plus 0, all times 20 seconds. Divide by 2. So 20 divided by 2 is 10. 10 times 125 is 1,250. The units, seconds cancel out. I'm left with meters. Meters is a displacement. That's looking pretty good. This is a motion quantity, so I'm going to highlight that in yellow. Part B. What is the plane's acceleration? And they're reminding us that this plane is moving forward and it's slowing down, so we're expecting to get a negative value for that acceleration. So part B, acceleration, and it would be in the horizontal direction. I forgot to do this earlier, but let's go ahead and show that the vertical acceleration would be 0. The forces are balanced. Okay, acceleration has that dual personality. It can be a force variable and it can also be a motion variable. I have an equation for acceleration up here, but I don't have enough information to use this equation, so I'm going to have to go back to my acceleration motion variable idea. And really, we have all sorts of givens. We can use any equation we like for acceleration. I'm going to use the one V final equals V original plus acceleration times time. Solve this equation for acceleration, so that would be V final minus V original, all divided by time. The final velocity is 0 meters per second minus the original velocity, 125 meters per second. And then we divide by that 20 seconds. So 125 divided by 20, getting 6.25. And then there is this negative, so that makes sense. So negative 6.25 meters per second squared. I'm going to dual highlight this quantity because it is a motion quantity and a force quantity. I want to remind myself of that. So part C, calculate the force which slows the plane. Well, that's this braking force right here. So now I can go ahead and use my Newton's second law equation. It says the negative force of the brakes is equal to the mass times the acceleration in the x direction. So the force of the brakes would equal the negative mass, 1,400 kilograms, times the acceleration, negative 6.25 meters per second squared. It's going to be a large force, but that makes sense. Planes are large objects, And so a large net force would be required to slow this plane to a stop. So the negatives cancel out, and I have 8,750 newtons is the braking force. And that's also the net force, because that's the only force acting on it horizontally. Part D, let's find the weight of this plane, the force of gravity. So the force of gravity is my unknown. I've got an equation up here with force of gravity, but I don't know the normal force yet, so I can't use that equation. But I can say that the weight is mass of the object times the acceleration of gravity. So 1,400 kilograms times gravity, 10 meters per second squared. So that's 14,000 newtons. Weight is in newtons. And then finally, part E, find the normal force acting on this plane. So what's the support force that the ground is providing to this plane? So normal force is my unknown. I have an equation up here that I can use. I know that the normal force minus the force of gravity is equal to 0. So the normal force is equal in magnitude and opposite in direction of the weight. So that would be also 14,000 newtons.